Okay, friends, it's 2:35, so it's time to get started today. Nice to see all your smiling faces and to hear our Tim have his usual conversation while I try to lecture. So nice to see everybody. So let's see here. In terms of course announcements and other things, let's see. So we have a homework due tomorrow. Thank you. So do your homework. As our colleagues in the front of the room have pointed out, this one actually requires looking at a research paper, which of course is a key skill as a graduate student here at MIT. So it's good to practice these kinds of things. So I think we give you three, right? The connection Laplacian, vector heat method, and the third one I forgot. These are all kind of fundamental papers in this area, and they're fun things to read. They're kind of cool constructions. These are also fantastic examples of things that are a lot easier in the discrete case than the smooth case, like just defining a connection Laplacian in a smooth differential geometry sense is an annoying thing and a little bit outside of the scope of like the machinery that this class has at its disposal, but doing it discretely is not so painful. Yeah, so it's a fun assignment, I think. I don't know. These are fun things to do. So beyond that, your projects should be, projecting. And that's about it for this course, I believe. Any administrative questions, comments, concerns? No? Okay. By the way, there was like some bug with the homework due date on Piazza or Canvas or whatever, but it's fixed, right? So we're good. Generically, whatever's on the course schedule goes. Okay, fantastic. So I think that's everything administrative. Everything here is pretty straightforward. Oh, also a bunch of your homework grades went out. That might explain why there's like a big empty chunk of the classroom here. But strangely, there's also a larger number of people sitting toward the front, which is, the dynamics of this over time are just fascinating. I don't know if it's like an intimidation tactic or something. I've been documenting very carefully over time. It's like one of those game of life situations in the classroom here. But in any event, the rest of this class, basically you have one more homework after this one and your final project. And don't forget that your project has a write-up component and a presentation. So Thea and I guess should probably figure out the presentation logistics sooner rather than later. So stay tuned. Okay. So that's all the news is fit to print on the organizational side. Fantastic. Right. So with that, we're going to continue our discussion of Laplacian. Last time I promised you the point cloud Laplacian. We're going to reshuffle because I got distracted reading recipes for ravioli last night and did not finish preparing our lecture on point cloud Laplacians. So we will defer that till next time. When I'm not, getting ready to make the ravioli this evening. And instead, we'll proceed as scheduled for this course here and then go back to one more discretization of the Laplacian next time, which I think will work out anyway because I was looking at the materials for this lecture and there are too many. So I think what probably makes sense is we'll get as far as we do today in our discussion of applications of Laplacian. We'll finish up next time and we'll also go back over the point cloud Laplacian from Misha Belkin's research in our next lecture. So we might fall slightly behind the course schedule, but I made the course schedule, so I get to do that. Cool? All right, so sorry about that. And if you're wondering, there are many recipes for ravioli, and they all are slightly different. I don't know if you have recommendations. I've got this pasta press, and I never use it. Okay, so we've spent the last several lectures basically defining a particular object and then studying its structure and then making it work on assorted domains. And that object in particular is called the Laplace operator. And we have studied the bejesus out of this thing, and that is because it was basically the most popular thing to study in geometry processing for the last 10, 15 years. Like there's a reason why we put so much time into this object in this course. And moreover, it's one of these things where like no matter what, like no matter where you start in geometry, somehow you end up at Laplace operator. Like it's just this thing that like is worth recognizing in the wild because it just shows up. And in almost all of your research, I guarantee you, somewhere if you squint enough, you'll find it. Or Tim gave me a little like, like a challenge, but we'll find it. But so in any event, this is just one of these objects that's worth getting a good intuition for. And one of the really funny things that I've noticed, like for instance, in the last couple of years, of course, deep learning, and now these days, like geometric deep learning are new popular fields, and they're rediscovering, yet again, all of our favorite formulas involving Laplace operators, just now coded with the nonlinearity on the outside. Like it's really just the same object once again. So it's really worth studying these objects in great detail and understanding every possible way to discretize them, how they behave, and so on, I think. And you're in my class, so you get it too. Okay, so we'll do a little bit of review of what the heck we've been doing for the last couple lectures, and then essentially our goal for today's lecture, and probably a little bit of next time, is to just go through a big grab bag of different applications. And one of the really fun things that we'll see is that now that we kind of know how to do some basic calculations with this thing, like we know how to construct a Laplace operator. In fact, I believe you coded one on your homework. You'll see that just given access to that matrix, like some very, for a while, people like me, my generation of researchers, were in this fun, like, jackpot research field where all we had to do is, like, take our favorite linear algebra function, built into MATLAB or Python, apply it to Laplace operator, Google the relevant theory for Laplace operators, and give ourselves another research paper on, like, oh, look at this cool spectral structure. Because it's just like there's so much stuff hiding in this one matrix. And that, we'll see that today. Like, we're going to go through, like, 10, 15 different research papers, each one of which is basically just like a few lines of code after compute Laplacian. And it's kind of neat that you can do that. And this is just a small sample of many. As a tiny bit of review, remember our sort of high-level story here is that essentially our Laplace operator was motivated by this question of can you hear the shape of a drum, where we have some shape in 3D. Like we've mostly been thinking about 2D surfaces embedded in 3D, but there's also like volumes and other things all have associated Laplace operator. And you knock on it, you hear the list of vibration frequencies that object makes. Right? And remember that this is sort of like a useful way to featureize a shape, right? Because shapes are complicated things to work with. They have arbitrary numbers of vertices. They can be laid out in all kinds of different ways. Whereas like the list of eigenvalues of Laplacian is just like a vector of numbers. And so for instance, for applications like retrieval, it's very easy to work with, the Laplacian eigenvalues, whereas it might be very difficult to work with the shape itself, right? That was the sort of intuition behind this domain. And what we've seen is that this isn't just like a clever hack. Like this is a pretty principled thing to do, right? For instance, it's very unlikely to encounter two different objects where when you smash them both against the wall, they make the same sound. So in other words, like this list of eigenvalues here is like somehow very informative about a piece of geometry. But not completely, because there do exist isospectral shapes. Incidentally, there's one little addendum to that story that I thought I'd mention. I've never seen somebody in computer science use this fun fact. If you're looking for ways to be a smartass at geometry processing conferences, one way to do it, of course, in reality, all the algorithms we'll see today, especially the ones that depend on eigenvalues of this operator, you never compute all the eigenvalues of the Laplace operator, largely because you can't. I mean, for one, you've discretized your shape as a triangle mesh. And what'll happen is for the really high frequency, at some point you'll transition from like meaningful eigenfunctions to things that just look like noise, that are like a byproduct of the fact that you're using triangles. So of course, all these algorithms are really approximate, right? Like they're typically built on theory that requires knowing an infinite number of eigenvalues, but the reality is you only use a finite number, right? It is worth keeping that in mind. And in fact, it turns out that there's a really strange theorem out there. I should remember to look, if you remind me, I can find the reference. But essentially what it says is if you give me any finite sequence of eigenvalues, I can basically come up with a shape where those numbers are the first n eigenvalues of its Laplace operators, which is a really weird and counterintuitive fact, right? It almost, but not quite, violates Weil's theorem, right? Like Weil's theorem tells me that like, I know the distribution of eigenvalues, like I know that they're like quadratic for a surface or something like that. But it only says that in a limit, right? So for any finite list of eigenvalues, I can always find a shape where those are the first however many eigenvalues. If you want a really nasty and mildly useless inverse problem to solve, it would be exactly that. Like you prescribe the eigenvalue, like can you drum the shape of a here, I think is actually apparently a tractable problem as long as you assume that your ear has only finite bandwidth. But that's mathematically the case. I think it's quite hard to do in practice. I actually don't know the graph theory version of that question, whether it's positive or negative. There's some interesting theory problems hiding here. In any event, we started with this, this sort of high-level picture here, and basically we reduced it after lots and lots of totally unrealistic assumptions involving what vibration frequency really means here, to this problem of computing eigenvalues of a very carefully chosen operator, namely this Laplace thing, which on a surface we figured out how to discretize in our previous lecture. That led us to a very famous matrix called the cotangent Laplacian. Remember that. Actually, I'll tell you. You tell me. If I have a triangulated mesh, and the only thing about it is I compute this matrix L, is that enough for me to approximate its Laplacian eigenvalues? It's a trick question here. The answer is no, right? Because remember, there are two ingredients you need. One of them is this. We call this the stiffness matrix, right? We're missing a second one, which is the mass matrix. Yeah, thank you, Marcel. Because remember that essentially when we take this problem and discretize it using finite elements, we end up with something that looks like LV equals lambda mass matrix times V. The number one bug that I see in this course and among all of my graduate students is missing that matrix M. In fact, just yesterday we were having this discussion with my student David, and he's about to graduate. So this is a very common scenario to be in. Okay. So from a theoretical perspective, that's the sort of story, right? That like the smooth Laplacian has all kinds of beautiful properties, and moreover, like it's just a formula to approximate it on a structure like a triangle mesh, and also on a graph, by the way. Moreover, if you remember back to like lecture 2 of this course, we were talking about just linear algebra tools generically. One of the things that I mentioned is that like the more structure you can add to the matrices that you encounter in numerical linear algebra, the better. Notice that the Laplacian matrix is like the prototypical example of what we call a sparse matrix, right? Meaning that most of the entries in that matrix are equal to 0, right? Like if we look back at this formula here, right, there's only non-zero terms if I and j are adjacent to one another. In fact, if you're really good, let's see if we can do a little bit of, what do they call this in like pedagogy, like synthesis? So let's take a look at this triangle mesh here. This is actually a very well-behaved bunny as they go, right? It looks kind of Delaunay. Roughly, on average, how many non-zeros per row should there be in this matrix? We have 1 vote for 6. Any other votes? Anna, explain your reasoning to us. So why do we think 6 non-zeros per row?
It's a closed mesh with the average number of vertices neighboring vertex.
Yeah, so remember a couple lectures back, we talked, it was several lectures back now, but I remember it fondly. We talked about how the average valence of a vertex on a triangle mesh is 6, but does that mean the number of non-zeros per row is 6?
I think it's 7.
It's 7. That's right, you forgot the diagonal term, but you're close. In general, like, let's say that I have a mesh with n vertices, then, rather than storing, n squared numbers, which is how we typically store a matrix, right? This one is really just like 7n values, right? Which is big savings. And that's why, like, in your code, if you forget to store your Laplacian as a sparse matrix, suddenly, like, your code will, like, grind to a halt, right? Like, and it won't scale to large meshes. Does that make sense? So this is just a fantastic example where, like, we started with geometry, and now we're just in, like, totally classical linear algebra land, right? And, like, using all of our favorite numerical algorithms. And, like, all the tricks that people use to speed up numerical stuff directly apply now to, like, analyzing a shape. Incidentally, I should pause here to advertise. In the fall, I'll be teaching a numerical analysis class in the ECS department targeted to late undergrad, early grad student. I desperately need TAs, both for this summer to help me prepare the course and for the fall. If you are interested, please contact me because I desperately need your help. Okay, right. So the next topic in this course, we'll talk about discrete Laplacian operators. Basically, we've done all this work to define this object, and in some sense, we haven't really talked a whole lot about how they're used in practice. We've motivated, some of the basic kind of mathematical questions people ask about Laplacians, but if we jump forward 100 years, like what do we study with them, in the well, largely the late 1900s, early 2000s. And these days, they're making a comeback. So in our lecture today, we're kind of going to go through 3 pieces here. We'll start by just reviewing some properties of Laplace operator that are going to suggest a lot of the applications that we encounter. This is mostly review from the last couple lectures. Then we'll talk about sort of low-dimensional applications in computer graphics and computer vision. And then we'll end with some applications in machine learning. And that we may defer to our next lecture depending on time. I'll try to take a look at my clock. Okay, so let's get started. In particular, let's talk about some useful properties of the Laplacian. I'm going to start kind of motivating why we might use this thing. And essentially, the thing to remember is that like the Laplacian is this one matrix that somehow has many different interpretations and uses, right? So if we go back to our graph Laplacian definition that we had 2 lectures ago, remember that we can write this very nice formula for the Laplacian where essentially, you know, maybe at least in this unweighted case, we have down the diagonal of our matrix the degree of every vertex and then just like a -1 for every adjacent pair. So from the perspective of this matrix, we can think of Laplacian as sort of like taking a value per vertex on a graph or on a shape and kind of saying like, what is this value relative to its neighbors? Does that make sense? Like somehow like I take the average neighboring value, I look at mine, and I subtract the two to compare, and that sort of tells me like, is this value bigger than stuff nearby or smaller? And indeed, as you take the limit and you refine your object, this is somehow, you know, some notion that's not unlike, you know, Hessian's or curvature, right? It's like a second derivative kind of quantity, which makes sense because Laplacian is the total second derivative. So this property, for example, is going to be useful in surface parametrization, where I map a surface into a plane, and a totally reasonable ansatz would be to take every vertex and kind of map it to the average of its neighbors, and we'll see that that is a strategy called harmonic parametrization. It makes sense, right? Because the term harmonic is thrown around a lot when we see Laplace operators. Okay? We also saw that the Laplace operator is intimately linked, basically through integration by parts. I need like a T-shirt or like a Superman kind of style thing here. You know, that essentially for every Laplace operator, there's this Dirichlet energy that's associated to it, which is measuring smoothness, right? So if I take an inner product of a function and its Laplacian, then by integration by parts, you know, up to boundary terms, essentially what we're measuring is this like total squared derivative of our function f, right? Which, remember, we use this to justify a few arguments. For example, if we looked at eigenvalues of Laplacian operator, right, like the low eigenvalue eigenfunctions sort of correspond to very smooth functions on the surface. Remember, we made that argument. Okay? Of course, Laplacian is also linked to a lot of physical problems. So, for example, the eigenvalues give you vibration modes. We'll see that it's also linked to heat diffusion, and even Schrodinger's equation can be written in terms of this operator, which is kind of nice, if I could ever remember what Schrodinger's equation tells me about life. And also, the Laplacian is sort of written, at least in the discrete case, in terms of very natural geometric quantities, right? So, for example, here's our formula for L and M. One small observation about this formula here. Now, take a look. So this is our favorite cotangent Laplacian. One thing you can immediately kind of notice here, let's say that I take my mesh and I just scale it. I just take all the vertices and I multiply them by 23. Specifically that number. Okay? 22 if you're, what, Taylor Swift. Then what happens to my matrix L? Stays the same, right? In particular, L only depends on angles, right? In fact, there's no length built into this formula at all, which actually is sort of suggestive of a property of Laplacian's, which is absolutely true, namely that it depends on what we call conformal structure. So if I take a surface and I somehow deform it without changing the angles of the triangles, which I can do, for example, by taking triangles and hinging them about a shared edge, then this matrix L just doesn't change. It does not sense changes in conformal structure. M does. In fact, if you're really good, if I take all the vertex positions and I multiply them by 2, what's going to happen to the Laplacian eigenvalues? Can you guess that one? I can never remember it. There's an area here, so you'll get a factor of 4. But I can never remember if it's 1/4 or 4. But anyway, I'll let you work that out. But essentially, like, you know, there's some simple scaling laws that are hiding here. And moreover, you know, these matrices are just built out of very simple formulas in terms of like angles. These are not complicated things. They're built out of stuff you had in high school geometry class. In fact, there are so many different equivalent formulas for this object. The cotangent formula is the most well-known one. And it's kind of interesting because the presence of cotangent here is just one choice. It's kind of funny that whoever did this 20 years ago, now we call it the cotangent Laplacian, but the reality is, like, we saw like all these trigonometric identities. There's like 1,000 different ways to write the same expression here. Here's another nice one. This is another kind of well-known formula. I borrowed the formula from one of my old papers, but I should be careful to credit that this goes back way earlier than this paper. This is where I know where to find it. So this one is completely in terms of edge lengths and triangle areas. And essentially, it's only useful just to know that essentially, from the perspective of this formula, for example, it's very clear that if I know the lengths of the edges of my triangle mesh, then I can construct the matrix L. Right? Right. So in particular, what happens to Laplace eigenvalues if I take triangles and I hinge them about a shared edge? We're going to see this example a lot today. Nothing. So immediately I know that I cannot reconstruct a shape given the Laplacian eigenvalues, extrinsically speaking. Right? However, there's a different question you could ask, which is, can I reconstruct the list of edge lengths of my triangle mesh? And that story is a little more complicated. Yeah? In general, the Laplace operator in the discrete case is very obvious, is invariant to deforming a surface without changing its edge lengths. And there are many ways to do that. Like, for example, if you have, let's say I have I have a triangle like that, and I subdivide it into 3 triangles like this. I take this vertex and I kind of pop it out of the board a little bit. I can make a completely equivalent version of that configuration where I take that vertex and pop it into the board by the same amount. So there are lots of ways to get like kind of isometric but different surfaces this way. But in general, this sort of intuition and the promise behind a lot of the Laplacian-driven algorithms out there in low-dimensional geometry was the fact that it is invariant to isometry. And in particular, a lot of the early 3D applications were driven by scans of human bodies. Right? And we wanted to, people would stand in front of the 3D scanner, we get some idea of their shape. Maybe in the early applications, they had to kind of do the hokey pokey and get scanned by this thing on all ends. And then the idea was that like, even if you're in some different pose, I mean, most of you are filled with bones. And because of that, I think that's a non-controversial thing to say, when you deform, the surface more or less is deforming rigidly away from your joints. Right? And so the sort of intuition here was that these Laplacian algorithms were kind of nice because you're sort of quotienting out human body motion because for the most part you're deforming isometrically. Right? And so this was the basic idea that if I want an algorithm that is invariant to bending without stretching, then maybe I build it out of the Laplace operator. Now this idea of isometry, there are many different definitions. This is sort of the most obvious one. An isometric deformation of a surface is one that essentially the distance between any points in geodesic terms is preserved under your map f. So like if f maps you from your straight arm to your bent arm, then this function d is roughly the same. Or, by the way, there's something called a local isometry, which is essentially just this thing in a differential form. It says that like f preserves dot products. These two are the same object. Right? And so there are all of these algorithms. In fact, if you went to the symposium on geometry processing, this conference whose deadline is in 2 days, it's still a popular one in geometry, I think I would say about 85% of papers in that discipline for a few years would start with this entire lengthy introduction section about how, any good geometry processing algorithm needs to be isometry invariant, and this is what's going to, sense the intrinsic structure of your surface. And of course, the hope here is pretty nice, right? That for a lot of cases, that really is the right thing to do. And in particular, if you're worried about algorithms that are not sensitive to human motion, that this is a good way to go. Of course, if I have a big data set of 3D humans and I ask for exactly the opposite of that, I say, search my data set for all of the people whose hand is up, then Laplacian-based technique would not be very good, right? Because that's like throwing that information away. So we'll return to that question a bit. Of course, the reality, theoretically, by the way, is that there are very few surfaces out there in the world that can deform isometrically. So you can, by kind of just constructing these little discrete cases, you can do it with triangle meshes easily enough. But even here, this is a very local thing, right? Like I didn't like make some big global, like articulated change to a surface. It's actually quite hard to engineer surfaces basically made out of toothpicks that can bend freely. This is a difficult thing, right? This is sometimes called like differential isometry as opposed to like global where you can like pop something in and out like what we have here. In fact, surfaces that admit this kind of deformation are typically called developable surfaces. And you may be familiar with that under a different name, which is origami, right? And in fact, it's really just intrinsically flat stuff that tends to be the things that can bend. Yeah? And sadly, human bodies are quite different than origami here. Right. So essentially, the high-level point here is that, essentially all we've shown so far is that if two surfaces are exactly isometric, then the Laplacian is preserved and our algorithm will succeed. The reality is if you want to do analysis in this space in 2023, then really you need to show what happens as you deviate from that case. And sadly, that's not an easy theory. It's easy to show that like Laplacian structure is sort of differentiable in perturbational changes to a surface, but like displacing your entire arm is hardly perturbational. And then things become very difficult very fast. And so I think a lot of people are actually revisiting these techniques to try and make them more robust, which is kind of interesting, modern topic to study and one that still there are a lot of questions. In fact, from a theoretical perspective, you can prove a few things. In fact, some of them are really counterintuitive facts about life. This paper on the left-hand side is one of the more widely cited research papers in this field. This is titled "Discrete Heat Kernel Determines Discrete Riemannian Metric." It's actually kind of a funny title to me because the discrete heat kernel and the discrete Laplacian are sort of the same. If you have one, you have the other. And they have this little innocent-looking theorem hiding in here. This is theorem 3.5. So suppose two Euclidean polyhedral surfaces, so that's basically like meshes, are given with their cotangent Laplacians agreeing. Right? That's what this L's are. Well, this is true if and only if they differ by scaling. And this is, I think, there's like some general position kind of argument here, but in general, the D's here are the lists of like edge lengths, right? So what is this saying? This is saying that two surfaces only have the same Laplacian, discretely speaking, if they have precisely the same set of edge lengths, just up to global scaling. If you know anything about the conformal theory of Laplacians, this is not true in the smooth case. There are like different smooth domains that vary by like bending but not stretching, or rather by conformal changes. So you change the angles, but the other way around. I'm going to abort that sentence and try again. Let's say that I have a surface and I deform it by preserving angles but not areas. So I can do things like curl it, but then they might squash, right? Then the Laplace operator actually won't change. But this theory says in the discrete case that doesn't happen. There's something special about meshing that gets in the way of that. This is an example where somehow discrete and smooth actually just don't agree. In fact, moreover, a piece of research that I got to collaborate on years ago even kind of gives a nice formula. If you have the mass matrix in the Laplacian for just, you can reconstruct the list of edge lengths by just two linear cells, which is a little funny. So essentially, this is some interface between smooth and discrete you have to be a little bit careful about. Moreover, I love this figure from this paper in 2010. All of the analysis that we've done so far is on 3D surfaces, right? And of course, 3D volumes also have Laplace operators. I could like tetrahedralize your hand and like talk about it as a piece of meat. But we haven't done that in this course, right? Like the cotangent Laplacian exists, but it's different. Here's a look up a different formula for that thing. It's a much bigger matrix because now you have to fill in all the space in between the sides of your the outer surface. And unfortunately, you don't get the same set of eigenvalues. The eigenvalues, so in other words, like if I have a thin shell, which is what we've been studying so far, the spectral problems associated to that thin shell are actually not the same as the spectral problems associated to a volume. And so some folks, including in our group here at MIT, have revisited some of the algorithms we'll talk about today from perspective of volumes. Because again, we keep talking about isometry invariance, or even near isometry. Like if I take a rubber glove and I bend it, what happens to the fingers? They probably just collapse, right? And from perspective of a rubber glove, that's very cheap deformation. From perspective of a volume, that's a very painful thing to do. And that gets reflected in the eigenvalue problems, that like they're just very different. So anyway, I encourage you to take a look at this old paper on volumetric HKS. I think was one of the very first papers to kind of realize, like, oh, wait a second, like, we all do geometry processing on surfaces, but the reality is, in computer vision especially, like the surfaces we're looking at are really boundaries of meaty things. They're not like just thin things made out of tinfoil. And maybe we should be revisiting the kind of invariances that we care about. It's really funny, these little subtle geometry processes, like these little subtle geometric invariances that we don't even think about get built into our algorithms. And then we don't think about them. And they're really explaining the good and bad performance, which is kind of funny. Whew. Okay, so anyway, to kind of summarize our discussion so far, if you want to know like why to study, and I should probably move this slide back a couple lectures, but if you want to know like why to study this object, we've shown, in fact, on discrete objects, we know that the discrete Laplacian gives you all of intrinsic geometry, gives you all the edge lengths. There's nothing more in it, right? If I have this thing, I have everything I could possibly want to know about my shape. Moreover, it's kind of multi-scale, right? Like if you do eigenvalue problems, there's like big eigenvalues, small eigenvalues. It takes geometry problems and reduces them to linear algebra, which is convenient because we have lots of software out there for dealing with linear algebra problems. And finally, there are lots of nice connections to physics problems, which gives some good intuition for why to work with this thing. So hopefully I've convinced you that this is a useful matrix. That's my basic point here. Okay, so now let's see how this plays out. So again, we're going to kind of divide into two. We'll talk about some applications in computer graphics and 3D shape analysis, vision, and then some applications in machine learning. We'll see how far we get today, and we'll wrap up next time. We'll talk about point clouds. And then we're going to do vector fields, which I'm terrified of because that math is hard. Okay, so here's a problem that is funny. Like a couple of years ago when I was teaching this class, I'd have to justify to graphics students. But these days, because we're so used to thinking about deep learning, I think this is the very first problem you think of, which is simply coming up with, it's funny, in the geometry community, they called them shape descriptors. These days, we've converged on the term feature because that's what's popular in vision. But there's basically two different things we might do. One would be to map the entire shape to a vector, which is kind of describing that shape. Right, we talked about that for retrieval. And remember that a totally reasonable choice there is just a list of Laplacian eigenvalues. A slightly different thing that we might want to do is map every point on the surface to its own feature, but in a way that's like comparable between two different surfaces. So for example, let's say I have this 3D bunny, and I just rotate the bunny, yeah? Then obviously like XYZ is not a very useful feature for a point on the surface because they all changed, right? So like if I want to compute, even if I literally just have two copies of the same bunny and I just forgot which vertex corresponds to which, right? I could not do closest point in XYZ space if they rotated for one another. So a different thing I might do is compute some feature for every point on the surface and then match them together in feature space. So for example, maybe I compute the Gaussian and mean curvature of every point on the surface, right? That's the sort of one thing we've done so far. And now we say, okay, well now I can at least match two rotated bunnies from between each other by just matching together points that have the same curvature, right? In the very least, that's rotation invariant, yeah? Of course, that's very noisy, right? Curvature is a local thing. So we'll see Laplacian allows us to sort of cook up descriptors or features that are multi-scale and tell us about the surface in a nice kind of smoothed out fashion, okay? So typically, when we talk about computing descriptors or features of surfaces, we usually want them to do a few different things. One is maybe characterize the local geometry of the point. The second one is to sort of describe that point relative to the rest of the points on the surface. These are geometric things. Of course, the third one that gets thrown around in computer vision is something, semantic, something. But the sort of learned aspect, typically, by the way, these are the features that go into your machine learning model, and then it just selects from among them. I would say 85% of learning on triangle meshes is built on the features we'll show you today, even though they're kind of buried in the first implementation details section. And we've already seen some features. So for example, here are two features, right, which are Gaussian and mean curvature. And we have talked at length in this course about how to approximate these two things. The only problem is that, like, if I take the ears of my bunny and I just make one a little bit shorter or something like that, these features won't sense that very easily, right? Because they're so local that this sort of global structure of the surface gets lost. Whereas, like, maybe if we look at low eigenvalues of the Laplace operator, we can do something more, right? That's the intuition. Okay, so desirable properties of a shape feature are usually that, like, 2 points don't get mapped to the same place, right? Because then I can't ever untangle them. That they're somehow stable to, like, deformation of my surface, for example. And again, if you read geometry processing papers up to about 2009, all of them would say that, oh yes, all desirable shape features should be intrinsic. They should only depend on edge lengths. Now we're revisiting that assumption, especially now that you can sort of maybe use a machine learning tool to decide, like, should it be intrinsic or not? But certainly that is a feature that sometimes is desirable. Okay. And of course, intrinsic descriptors, just to repeat myself, are sort of variant under these things. Okay, so give me an example of an intrinsic feature for a point on a surface. We've already seen one. Yeah? Gaussian curvature, that's absolutely right. If you remember Gauss's theorem here, right, we didn't actually prove in this course because it's a little bit complicated, but we quoted a theorem that said that Gaussian curvature only depends on the metric of the surface. And indeed, if the surface bends without stretching, the Gaussian curvature does not change. So we have one, we have a scalar. Now, surfaces are two-dimensional, so we need at least one more before we'll be able to use these features to characterize points. Yeah, Marcel?
Normal vector?
What was that?
Normal vector or something?
Normal vector is sort of the opposite of intrinsic, right? It's a point. In fact, in some sense, the normal vector is chosen to be the most extrinsic possible object on a surface, right? It points right off of it. What was that? Mean curvature is not intrinsic. So I'm like, sorry, I almost took my shirt off to demonstrate, but gosh, all the paper in this room is like taped onto things. Here's a sheet of paper. You know, if I bend it like that, the mean curvature changes, but obviously this is intrinsically flat. So yeah, nope, not quite. Any other guesses?
Okay, does it have to be something? Is it something that we're already seeing?
No, because we haven't seen anywhere.
I think it's going to be around the kernel signature.
Yeah, heat kernel signature is one. So anything built out of the Laplacian, right? You could maybe try and build something out of heat. And indeed, there's a lot of reasons to do that. A different kind of issue here. Here's Gauss curvature on this innocent-looking surface that geometry processing people like. It's titled fertility, which always kind of weirded me out. But in any event, this thing, you can see that even though the surface like looks very smooth, when we apply this very standard approximation of curvature, you get this very messy function back. So you can imagine, you know, algorithms that are built on this kind of calculation get very noisy and hard to work with. And partially, by the way, that's like, you can kind of see it here, like the triangulation of this surface has these big triangles that are kind of slivery and cutting across. And moreover, you know, curvature doesn't distinguish points on the surface. For example, all the points on the top of this car have roughly the same Gauss curvature, so this is clearly not sufficient for a feature. Okay. So we've had all these desirable properties. We've already seen them so far. What are we to do to compare some points on a surface to one another? There are many different features out there that are all built out of the Laplace operator. So we're going to kind of go through them in roughly historical order. They all have the same theoretical properties. So what's a little bit tricky is that, like, you know, there's theory and there's practice, and we'll see the ones that get used. And I think we're lacking a little bit. Like, the theory students here should try and figure out, like why are some of these more informative than others in practice? I think is largely not well understood. Yes, Marcel.
You mean anything like higher order that is similar to Laplacian? Or
You could, but let's define what we're going to do with the Laplacian first, and then we'll come back to higher order stuff. Yeah. Higher order operators tend to have curvature in them somewhere. So that could be harder to do, and they're tough to approximate on the surface. But not all of them. Like the bi-Laplacian is just Laplacian squared. If you think about it, the eigenvectors of that are no more interesting than Laplacian, though, up to boundary condition. Okay, so historically, probably one of the very first features to be cooked out of the Laplacian operator is something called the global point signature, or GPS, which I thought was cute. This was proposed by Raif Rustamov in about 2007, which is like roughly the happy golden age of Laplace operators on meshes. And essentially, what Rustamov here proposed was a very simple feature for a point where I compute the Laplacian eigenvalues and eigenvectors. So the eigenvectors here are the phi's, the eigenvalues are the lambdas, associated to the surface. And I map every point on the surface essentially to just its list of Laplacian eigenvalues scaled by 1 over lambda. Notice the scaling here is kind of good because lambdas are frequencies, right? So as lambdas get big, this 1 over square root of lambda goes small. And it probably makes sense to upweight the low frequency because those are the things that we can measure with the most reliability, which is kind of what's going on here. Does that make sense? Okay, so why was the global point signature a positive thing? So for one thing that you can show is that this GPS signature here does have the property that if you have two different points on a surface, they necessarily have different GPS coordinates. Isn't that cute, GPS coordinates? Ah, you guys don't appreciate anything. Right, so the basic point here is that it actually, there's kind of a funny caveat here, which is your surface doesn't self-intersect, then neither does the GPS embedding, and the proof is actually one line, which is kind of clever. Remember we mentioned that the set of eigenfunctions of Laplacian spans L2, meaning if I have basically any function on my surface, I can write it in this phi basis. So think about what it would mean for 2 points to have the same GPS embedding. That would mean that every single eigenfunction of Laplacian agrees that that's 2 points, right? Well then, as a counterexample, if I cook up a function which is like 1 on one of those points and 0 on the other, I couldn't write that function in this basis, right? Because they always are the same. So there's your contradiction. It's just like a one-line proof. So for example, the GPS signature can be kind of handy. It's got this property that all points are distinguished from one another. Moreover, it's isometry invariant because Laplacian is isometry invariant. Almost all research papers in this field have a theorem that is basically stated like this and has a proof like that. Yeah, so right. So the GPS was one of the early ways to use Laplace operators to distinguish points on surfaces. And it was useful for comparing a surface to itself, like clustering points together, for example. Any idea what could go wrong? Like, let's say I wanted to use this. Like, I have Homer, and I've got all the eigenhomers here, and maybe I like get Homer in a different pose, and I do the same GPS, and I say like I want to match points. So like I take a point on his hand, and I compute the GPS coordinates at this point. I take my other surface, I compute its GPS coordinates. I just find the closest match. What's going to go wrong? Any idea? What's an issue with this algorithm? Symmetry is one, right? So if I had a repeated eigenvalue, like we talked about last time, that could be an issue. That's actually an issue in a lot of these techniques. Any others? Think about eigenvectors for a second. What do we, when I compute eigenvectors, like if I ask, I cook up a matrix and I hand that matrix to, Zoe and to Leticia, and they're not allowed to make eye contact because then they communicate. And they compute the eigenvectors of that matrix. Will they get precisely the same list of numbers? We're shaking our head. Why not? Change of basis isn't quite right. Like the basis is sort of determined by the matrix. Scaling is one issue, so you got me there. So let's say that I tell them they've got to be unit length.
Just have the one of the eigenvalues corresponds to, they're not unique eigenvalues. You have one that has a space that's higher than one dimension.
Let's maybe make this game even easier. Let's say I give you the following matrix. 1, 0, 0, 2. So there's no repeated eigenvalue. I hand this matrix to Leticia, to Zoe. They don't get to communicate. They give me back eigenvectors. And I tell them they have to be unit length. Are they going to give me the same answer? Sign. Thank you. Right? Eigenvectors are only known up to sign, even if we make them unit length. Notice, that's a problem here. Because each of these phi's, if I put minus phi, like there's no canonical way to choose a sign for an eigenvector. That's not a thing, which is problematic. Yes, or Chip? But it's not just symmetry. Even if you have a completely asymmetric surface, I just don't know the eigenvector to sign, right? So like even if there's only a single eigenvalue, only a single lambda with eigenvalue lambda 1, I still only know this value up to its sign. And if I take its absolute value, then all the nice theory we had in the last 2 slides goes away. It's actually not clear that we can do that anymore. And it's not differentiable. So the GPS was a nice kind of early example, and it's fine for comparing a surface to itself because then you're kind of doing apples to apples. But like comparing across a data set can get a little bit tricky. You need some engineering to make the signs of these functions agree somehow, and it's really not obvious how to do that. Yeah. So naturally, the community went back to work. This was 2007. We had a lot of time on our hands. It was a simpler age. And we looked back at different applications of Laplacian, and we said, aha, so the GPS, like, can you hear the shape of a drum is a useful formalism, but it has this issue that, like, eigenvectors only know up to sign. But the good news is that there's plenty of things in physics that are built out of Laplacian, and physics doesn't have a sign ambiguity. In other words, like, if I run a physical system, at least from classical perspective, it's deterministic. Like, it's not like, I diffuse heat and suddenly it like flips inside out or something like that. And so, in particular, the next most popular feature built out of the Laplace operator was built on a very particular partial differential equation, which is shown on the slide here. This is du dt equals minus Laplacian of u, right? So u is given as a function on my surface at t equals 0, and then I can involve it in time using this thing. By the way, in this notation, typically we think of, just to be totally clear, this Laplacian is in space, right? There's not a time variable here. You could imagine a different version where it's that plus the second derivative in time. But it's not here. So what is this equation, Leticia? It is a PDE. What's its name? The heat equation. Thank you. So this is the heat equation. I only call on people when I know they know the answer to a given question here. Right, so this PDE is the heat equation. It basically is governing diffusion. Here's a very simple example. So you have some distribution of heat, and there's how it evolves over time. Incidentally, there's a second PDE we'll return to in a minute called the wave equation. The only difference here is whether you have the first or the second derivative on the left-hand side, okay? So we talked a little bit about this a few lectures ago, but one thing that's worth remembering is that if I have the initial conditions of a PDE, then I actually can solve it in closed form in the Laplace-Beltrami basis, right? So in particular, if I have these functions phi n, remember they're associated with an eigenvalue lambda n, then one thing that I can do is I can take my initial conditions, like u naught, and then just take their inner product with each of the phi's. So this is like writing my initial condition in the Laplacian basis. And then if I want to evolve it forward in time, all I have to do is put a factor of e to the minus lambda t here. Notice, sanity check. What happens if I put t equals 0? What happens to these exponential terms? Yeah, they go away. They're just 1, right? So we get back to the initial condition. Does that make sense? So this is the heat equation, and the good news is that like solving the heat equation is really, really easy to do in this basis. Now, there's one very special case for the heat equation, which you can kind of eyeball here. Do I want to eyeball it here? I do. Okay. So let's say that I put a tiny, tiny pinprick of heat right at a single point, like x naught. So in other words, I have this function which is basically 0 everywhere, and then just really, 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 really peaky at just one point x naught as my initial condition. Okay? If you remember your electrical engineering class, you called this a delta function. If you took a math class in analysis, they told you delta functions are garbage, but there's something called a delta measure, which is basically the same thing. But in any event, a delta function is nothing more than a function where you've integrated against something else, it picks out its value at a point, right? So let's say that I put, for my u naught, I put delta at a point like x naught. Then what are going to be my ANs here? Yeah?
I think they're all going to have value, or they're all going to be non-zero. And that's like the...
Yeah, they're going to be a non-zero, but specifically what value are they going to be? What is this?
The value of the eigenfunction lower.
That's right. It's just phi n evaluated at the point where I put my delta. Does that make sense? Okay. So, in other words, let's see if we can kind of reinterpret this formula a little bit. By the way, I'm doing this off the top of my head, so there's some likelihood I'll get myself confused. Okay, so let's say that I put just like a little, pinpoint heat at some point x naught, right? Then what we just kind of argued is that an, in this case, is going to be equal to phi n of x dot, like that, right? So from this perspective, now let's go to this closed form formula we have on the top here, right? And we can sort of say the following, which is the amount of heat that diffuses from x naught to x in time t. Okay? Let's say I wanted to compute this value. What does that mean? That essentially I'm putting a delta function of heat at time 0 at x naught. I'm diffusing by solving this PDE to time t, and then I'm evaluating it at x. Does that make sense? So, in particular, what is going to be our expression for u? We can just plug into this expression on the board here. So u is going to be the sum over n of an. Notice that an in this case is phi n of x naught, like that. Times e to the minus lambda n t times phi of x, like that. That makes sense? Now, there's one special case of this. This object, by the way, if you think of it, you can think of this as the following. Usually we write this as like u of x naught x t, right? That's like, it's a function of these three variables all at once. This is like the amount of stuff that goes from x naught to x in time t. Yeah. This sometimes is called, like the Green's function or something like that. Okay. There's one special case, which is the amount of heat diffused from x naught to itself in time t, right? So x naught to it, that was supposed to be a t, sorry, itself in time t. Well, what's that? Well, that's going to be just a function of u of maybe x naught comma t. Now there's no x anymore, right? And all we have to do is just set both of those equal to x naught, right? So this is the sum over n e to the minus lambda n t phi x naught squared. Cool? This is fun. These are like easy calculations. This is nice to do. I didn't even bring notes today. Okay, so right. So this is a function. It is built out of Laplace eigenfunctions and eigenvalues. And for one, let's think about it for a minute. Like what do we expect this thing to do? So let's say that I have a lot of curvature versus a little curvature. So like think about Gaussian curvature. So let's say that I'm like very, very negative Gaussian curvature. So we have a surface that's like very saddle shaped. It's like kind of ruffly. Think about like that Shakespeare collar. Yes, Anna.
You're going to be diffusing more heat. There's more places.
Yeah, there's kind of like a lot of surface area, right? Like if I have that roughly Shakespeare collar, there's like a lot of different places that the heat can go, right? So diffusion will happen very quickly. Whereas if I have like a very pointy surface, there's not a whole lot of place for the heat to go, so diffusion might happen more slowly. So intuitively, this object actually has something to do with geometry, right? Moreover, let's say that I fix some constant for t. So I think of this just as a function of x naught. Notice that for every t here, what is this thing? This is an intrinsic shape feature. Does that make sense? Because it's just a function of x over the whole surface. Okay, this object has a name. Laetitia predicted it before, which is why I thought she might know the name of this, this PDE, also because I happen to know she studied it in the past. And that thing is called the heat kernel signature, or HKS of the surface. This is the most commonly used shape feature on 3D meshes. The HKS is just this closed form formula here. So typically in practice, when we want to compute this thing, we just truncate the sum. We like compute the first like 100 eigenvalues eigenvectors of Laplacian, and we just stop the sum there. And notice that that's sort of a reasonable thing to do, because remember that the eigenvalues here go off to infinity. And what's e to the minus infinity? Well, it's a very small number, whatever it is, right? So basically, we're just cutting off the values that are close to 0. Okay? This is a really interesting shape feature, because for every single t, it gives you a different function on the surface, right? So in fact, it's a really funny, like usually we think of features as like mapping points on the surface to like a vector of values, right? Like the GPS is one example. This is actually mapping points on a surface to an entire function of t. Right? It's like a little plot that sits over every point on the surface. Now in reality, we maybe sample a few t's, but like that's the sort of theory here. Does that make sense? Is there any sign ambiguity here, unlike the GPS? No. I mean, you could have gotten that from the physics, or just the fact that there's a square. So we kill it. So in fact, if we ran our eigenvalue solver, we don't have to worry about whether we got plus or minus the same eigenvector, because we're going to square it anyway. Okay? Sneaky. Okay. So let's see a picture of what this thing looks like. So here is heat kernel signature. Here's our favorite 3D dragon doodad. And here, I believe Max has marked 4 points, 1, 2, 3, 4. 2 are on the, I want to say the fingers and the toes. Is that anatomically the right terminology here? Do dragons have fingers? We're going to save that for later. But the front toes and the back toes. And on the right-hand side, we're showing the HKS. Remember, these are a plot for positive t. I guess here you could extrapolate to negative t, but it would be unstable. It's not a thing you should do. Okay. And notice that these two plots kind of cluster, right? And this makes perfect sense. Essentially, this thing is clustering the front feet versus the back. Now, we had a question about symmetries earlier. Notice that this particular feature does not have the property that we had for GPS. Namely, if I have a perfect symmetry of the surface, then the heat really does diffuse exactly like identically in these two things, and they'll have the same GPS coordinates. And in fact, this was an early algorithm for symmetry detection, was just clustering in this space. I saw a hand and I forgot. Yes, Laetitia.
I was just going to ask, because you sound like the symmetry detection algorithm super well posed. What's the issue of using HKS for that?
Well, it depends on the problem you want to solve. So if I have a surface like human, it's perfectly symmetric. I'm a bad example. Then you cut it in half. If I have 2 points, like the tips of 2 fingers, they will have precisely the same HKS, right? In some applications, it's a good thing. Like for instance, if I want to find the left-right symmetry of my surface, then I just have to find pairs of points with the same HKS, and I'm done, right? On the other hand, sometimes, like for surface correspondence, like I really want to distinguish left from right, and this feature isn't enough. I need some other feature that knows about orientation. Yeah. Even orientation for some, like if you had a starfish, wouldn't be sufficient. Yeah. Any other questions? Yeah.
I guess I'm a little confused about why those graphs go up over time.
That's actually a reasonable question. I get your point that it's I think the reality here is that if you went all the way, yeah, aha, okay. This is log t. So in particular, we do not see t equals 0. What would t equals 0 be? Is a delta function, it would be infinity. So actually, this is a function that only makes sense for strictly positive t. And there it can go up. Like for instance, I mean, like kind of intuitively, like, heat could diffuse out and then kind of wrap around the surface and come back. Of course, it's not that simple because diffusion is like this fuzzy process. But like, you know, if you think of diffusion in the Brownian motion sense, like a particle is kind of wandering around the surface in a random way, then it most certainly could go back to where it started. Yeah.
I guess I maybe don't quite see that from the equation on the board, which is like as t, sorry, on the slide. Which is as t increases, shouldn't everything just go to 0?
As t increases, should everything go to 0? Oh, I see, because I'm just decaying. You make a good point. Let me think about this for a second. You're saying because essentially this coefficient is less than 1, then like this, yeah, you're right, actually, now that I think about it. That's right, so I'm guessing what's going on is this phrase, scaled HKS. My bet is what happens is for every fixed t, well, I was going to say they normalize it to square integrate to 1, but that would still give you the same. That's a good question. I don't know. That's one of these people that's not paying attention. Artem, look up this paper and see, why does this plot increase? Let us know. Yeah. Okay. You got your laptop there. Be helpful with it. Okay. So right. So yeah, that's a fantastic question. Now that I think about it, what I said is completely false. So it shouldn't go back up from this expression. So it must be that, like, maybe what they do is they say for a fixed t, you look at this function and then you just divide it by its L2 norm or something like that. It was funny in the years of teaching this. I never really thought about it. I don't know. Well, now you threw me off. Okay, yeah, I don't know. It's a fantastic observation. Yeah, I don't know. I'll have to think about it. I mean, yeah, my guess is there's some normalization happening here at every time that's changing, but that's a good point. Okay. Right, so let's see here. So it's an isometry invariant. It's multi-scale in the sense that small t obviously involves very small neighborhoods on the surface. Big T involves, you know, like now diffusion has happened over the whole thing. In fact, there's a nice little theorem. You can actually recover the Gauss curvature of the surface by taking a limit of this expression as t goes to 0, but you have to divide by a very careful factor to make that work out. That's also not a good algorithm for actually computing Gauss curvature because, of course, as t goes to 0, the large eigenvalues are the ones that dominate here, but those are the ones that we can't compute reliably because they depend on like discretization of the mesh, right? That's like high frequencies. It's not subject to this switching, like this sign issue that we talked about. They're easy enough to compute, and there is this relationship to curvature. In fact, if you look at the original paper, there's a formula. Did you find it? I'm just giving you a hard time. Okay. Yeah. There are still some issues. You know, if there's a repeated eigenvalue, then which like, corresponds to symmetry, like we talked about, then 2 points get mapped to the same place. And once again, it's important to keep remembering that all these theoretical properties that are so nice depend really strongly on having isometry. And the reality is it's just really hard to find isometric pairs of surfaces out there in the wild. You'll notice that the data sets that people used to test on when we were working on these problems, myself included, are very well curated shapes. They're like smooth surfaces of 3D cats that undergo slight deformation. And even there, it's a very hard problem. These days, these big messy machine learning data sets, obviously we have to do much more work to make these algorithms function. Okay, so this is the most widely cited and used shape feature out there in the literature, including now in the deep learning universe, by the way, because deep learning, you still have to contend with a mesh structure, so which most 90% of algorithms don't know how to do. So the very first thing they do is just map the surface to like its heat kernel coordinates, and then just apply deep learning to those because you don't have to worry about connectivity anymore. So it's important to remember these features haven't gone away. They're still the baseline kind of object that's used in these techniques. There were some other extensions. One of the most widely used one was actually it's kind of interesting, was that this ICCV workshop, it's like not typically the place we look for research papers in this domain, but for whatever reason, just empirically seems to be the best shape feature you can build out of Laplacians for a lot of the computer graphics data sets. This is we had the heat kernel signature. This is the wave kernel signature. A small detail here is that this is the wave equation from the Schrodinger perspective, so it's not quite the one that we saw in some earlier slides. But this is just some other PDE that you can solve in closed form with Laplacian, just like we kind of did here. And they just follow exactly the same formula to get a feature per point. And every property the heat kernel signature has, this one has too. It's just somehow the values are kind of reshuffled, I guess you could think of, like as a function of t here. They argue kind of spiritually that like maybe the wave equation is better because heat diffuses. So like for large t, HKS isn't super informative. Like information is sort of stored in high bits of a value, whereas waves just continue to ping pong back and forth across the surface for large t, which intuitively kind of makes some sense. And in fact, they show in their paper that like it's somehow more sensitive to local features. So for example, here is like HKS versus WKS at a large time, and you can see that WKS is like sensitive to wrinkles on his pants here. Now, essentially the properties here, we're gonna return to lots of slides that basically look the same here, just like lists of good and bad features. They're basically the same as HKS. The only negative here is that this thing now is very locally oriented rather than globally, so. Okay. So this is one of these things that looks like math, but really just engineering. Like essentially there's like lots of different PDE you can solve. For each one, you could cook up a different shape feature, and they all have the same properties because they all come from the same source. Yeah. Okay. So our high-level point here is there are so many objects. In fact, generically in the literature, we call these spectral descriptors or spectral features, which can be built out of just computing Laplacian eigenvectors. And so long as you remember to square, then at least you don't have that sign issue, and it really is a totally reasonable way to featureize the surface. Does that make sense? In fact, a couple years ago, some of the earliest work on 3D machine learning was built on precisely this observation. They looked at the solutions of all these PDEs, right? All these like X kernel signature, you know, heat kernel signature, wave kernel signature, and then they started doing like affine invariant wave kernel signature and like, you know, whatever, where you just build different PDE on surface and solve it and follow this formula. There's a really clever idea, which in retrospect is super simplistic, which said, okay, all of these PDEs, actually their kernel has the same form. Like if you take a look at this formula on the board, what is it? It's some function of lambda multiplied by phi of x squared summed over the different indices of the eigenvectors. And if you look at the form of the wave kernel signature, you'll see it's exactly the same. It's just that there's a different function of lambda here. It like has to do with cosines and sines, right? So Lippmann and Bronstein back in 2014, as the Middle Ages, as far as you guys are concerned, proposed a really simple machine learning problem. They said, okay, fantastic. So all these different PDEs basically have a kernel, which is just some function of the eigenvalue multiplied by phi squared. So why not learn that function f given data? And that's precisely what they did. So I believe the details of this paper are, in this case, they have a slightly unrealistic data set. Like they have a bunch of 3D models and a bunch of points that are marked that they know are the same on those models, which they kind of need in order to make those f's agree with each other. And then they just solve regression. And this is like the world's simplest machine learning problem in that like, notice the function that they're learning f is a function of one variable. This is very different than the machine learning models that we think about today, right? And already it was, by the way, pretty sufficient to do a lot of geometry tasks. Like, I remember there are two papers that kind of came out at similar time, this one and this point net model for point cloud 3D processing, which is something we might cover later in this course. Both of them are wildly simplistic. Right, like the machine learning here is 1D. We think of, you know, like deep learning as this very high dimensional process of like chewing up images and so on. This is just a 1D function. And similarly, like PointNet does this really weird symmetric operation, which is a fancy phrase for summation over the entire point cloud. And I remember having this conversation with Max Ozyonikov, who's another person like me that's worked on these fancy spectral descriptors for years. And both of us kind of came to the conclusion like, oh, like maybe geometry problems aren't so hard. You know, like somehow very little learning is needed to solve some of these basic things that we were after for many years, which is exciting and also mildly depressing. But in any event, this was a very early attempt at learning from geometry. And it's kind of funny because we talk about geometric deep learning as this very fancy machinery, but this is a case where the very first thing you do is quotient out the geometry and just reduce it to a one-dimensional kind of linear algebra problem. And in fact, actually, I can share one research paper from our own group which just generalizes that model slightly and says like, well, maybe the thing that I need to learn that is complicated is the Laplacian operator itself is this intrinsic thing, but for some problems, maybe intrinsic geometry isn't the right structure, so I should learn the operator while I'm at it. Then suddenly your math gets a lot harder. And now that's like the kind of problem that a lot of us study today. So I can refer you to that thing on your reading assignment if you're curious. There's a lot of yucky math in there, I know, because I wrote it down. Okay, to go back to our applications of Laplacian, we can continue to do many other ones. So for example, a different thing that you can do if you have the heat kernel signature at some fixed t is look at its local maxima. So these are like kind of points where like heat has trouble escaping or something like that. And it turns out these are useful feature points on surfaces. They tend to be quite stable. So sometimes for like finding fingers and toes or points of armadillo tails, this can be a useful technique, which is kind of a handy thing to do, especially in some computer animation scenarios. Like maybe that's where you place the handles for, deforming this object. Later on in this course, we're going to talk about correspondence problems, where I'm given two shapes, and my task is to find a mapping. So like maybe I spend a lot of time painting a texture on the first armadillo, and I want to transfer it to the second one. And it turns out Laplacian is built into that quite a bit. In fact, the simplest way to do it might be I take my two surfaces, I compute the HKS at every point, and then my map is just matching closest points to one another, right? Like just two, like a point on surface A and a point on surface B. Oh. Best apps for finding your perfect match. So it's a different kind of mapping problem. I'm better at these ones. Okay, so right, so we have a surface undergoing some deformation. I want to come up with a map, so like I point to like some point on this guy. My other guy is in some other pose. I want to find the same point on the other one. Obviously, I can't just rigidly align those surfaces anymore because they've undergone some weird motion. But I could take every point on the first surface and compute its HKS, every point on the other surface and compute its HKS, and match those together. And that was actually one of the early surface matching algorithms, and does reasonably well for surfaces that are basically the same. For after you apply some deformation, then a little bit less so. So this was, of course, given a name back in the day. We called this descriptor matching. Some of the deep kind of learning algorithms, by the way, for shape mapping are nothing more than this, where you basically backpropagate through the feature so that it is good for closest point, right? Like that's essentially what some of these algorithms are doing. One very simple example of that, which always gets confused with the heat kernel signature, is something called the heat kernel map, which is almost the same but not quite. So the heat kernel map was proposed by basically the same set of authors permuted around a year or two after the heat kernel signature. And this was used for, rather than like things where you just want to featureize the surface, this was specifically for mapping purposes. And so essentially they propose a slightly different feature, where they say, like, let's say I have a 3D model of myself, I have a 3D model of Matthew over here, and moreover, I give you one piece of information, which is I point like to the tip of my nose and the tip of his nose, and I say that like those 2 points should be matched together. Okay? So what the heat kernel map does is it computes a new feature. So here, this KT thing, this is the amount of heat that goes from P to X in time t. This is a slight reshuffling of the notation we had on the board. So remember, what does the heat kernel signature do? It puts 2 X's here, right? But now we have a special point. I know where Matthew's nose is. It's true. So given that special marked point, we can now construct a feature which is for every other point on the surface and for every time, how much heat diffuses from my nose to every other point on the surface as a function of t and where that point is. So in other words, if I slice through my heat kernel a different way, right, then for every t and for every x, I can compute this thing relative to that fixed point p. Does that make sense? This is not the heat kernel signature, right? The heat kernel signature would have basically the same point twice. Okay. So this is one of the earliest algorithms for correspondence of triangle meshes, and they actually prove kind of a neato theorem, which is kind of shocking and weird, which is the following. Under pretty weak assumptions, if I mark precisely one point between 2 surfaces, this feature is provably sufficient for matching 2 surfaces to one another. This is kind of surprising. So in other words, like if I compute that feature I just talked about, so we match our one point to each other, and now every other point on the surface gets this little vector of values, like how much heat diffuses from P to T as a function of T, P to X as a function of T. Have I lost you all? I probably have. No? Good, thank you. See, he shook his head, that's great. Then just doing that with one match point is enough to compute a map.
It says isometric matching.
That's right. So,
Isometry between me and you, I guess.
it's true, we are nearly isometric. No, so that was the assumption. If you look at the examples in this research paper, you'll notice that the surfaces are like this elephant, and then this elephant with its trunk like slightly bent. And the reason is that, again, it is so hard to compute or to find isometric surfaces in the wild, and that when that started to deviate, they had some tricks for fixing it, like maybe instead of one source point, you mark like 10. But then theory and practice don't align anymore. Like it's not clear that that actually helps in practice. Like we heard to prove a theorem that there's some stability there. Anna.
Sorry, what is the theorem exactly? Because if I give you two spheres and I match 2 points on them, you can rotate one of the spheres and it's like the signature is the same.
That's right. So the theorem is you only have to match 1 point under the assumption there are no repeated eigenvalues. Yeah. So yeah, you're right. There's a lot of assumptions that have to go into this theorem. There's no repeated eigenvalues. The surfaces are perfectly isometric, and no self-intersection, I believe, is what you need. Yeah. Good critical thinking. That's exactly the right counterexample. Yeah. Any other questions? Fantastic. But the good news is that like somehow we keep vacillating in this geometry community. Like is mapping an easy problem or a hard one? From perspective of this paper, it's a very easy problem if your surfaces are isometric, right? This is just a small calculation to do. We talked about before, a slightly different problem will be symmetry detection. This is easy enough if your surface is perfectly symmetric in an extrinsic fashion. Like the guy on the left-hand side, I could chop him with a plane, flip points over the plane. And algorithms like what, Ransack are very good at finding that symmetry axis. But of course, this person arguably has a symmetry, but it's intrinsic, right? It has to do with the distance function along the surface. Like there's no plane I can cut the surface with and get a perfect copy, right? So yet another research paper in the same domain basically used, and if you look historically, this was published in 2008, so there was no heat kernel signature yet, but they could have easily done it in that space as well. Just by clustering in GPS space, they find these discrete these discrete intrinsic symmetries. Okay, so notice that like we just went over about 9 papers in geometry processing in 10 minutes. Like these are all just like compute the Laplacian, compute its eigenvalues, evaluate some formula, and then you're good, right? Which is nice. Yeah. So essentially, that's our high-level point here. Laplacians are just everywhere in shape analysis and geometry processing. They're just like inescapable. In fact, here's a grab back of some more, just in case I haven't convinced you yet. Here's another one. Let's say I want to compute a distance between points on a surface. Not the distance, but a distance. So like a thing with a triangle inequality. We've seen 2 examples in this class. One of them is the square root of x minus x naught squared plus y minus y. You know, just like distance in 3D. A second one we saw was geodesic distance. Here's a third one. This is called biharmonic distance. So what you do in biharmonic distance is you choose a point on the surface, and maybe you in this case, I believe it's just Green's function of the Laplacian centered at that point. So you look at like, you invert L, and you look at the corresponding column of L. That's some function. And now, for 2 points on the surface, those give you 2 functions on the entire surface. We call those GP and GQ. And you just do L2 distance in this space. So in other words, you kind of like, it's kind of like taking the surface, mapping it to like HKS space, and then computing distances in HKS rather than distances in 3D. Does that make sense? In this case, it's not precisely HKS. It's inverse of Laplacian, but same difference. Yeah?
Why would you want to do that?
That's a fantastic question. Why would you want to do this? So for one, this is an isometry invariant distance, which is a, so if I want to compare points on a surface in a way that like isn't going to depend on how I deform, then I can use this thing, and it's arguably much easier to compute than geodesic distance. So there's some kind of trade-off. More or less, by the way, you can see, so here they're showing you level sets. It has some relationship to geodesic distance. You can see that they're kind of similar to one another, but they're definitely not the same. The other thing that they argue in this paper, which is kind of interesting, it's interesting to think about. Like there are a lot of applications of geometry that need a distance, but it's not clear it needs to be the distance. And they argue that actually if stability is what you care about, then this might be a better choice. Why do they argue that? Probably because they have this formula and they want to use it. But don't tell Ray if I said that. But it makes some sense. So in particular, there's some interesting theory out there for Laplace operator. And there's a phrase you hear in PDE, they call it small neck. And it's not just to describe your instructor, it's rather a theory that has to do with like if you take two surfaces and you kind of glue them together at like a little tiny interface. So you just like, I've got a sphere here and a sphere here, and then I just like create this little itty bitty like interface between them to make a new surface like that. Now, if I compute a lot of quantities, they change drastically when I make a change like that. So for example, let's say I have a single surface that looks like this, right? And I add a small neck that connects, so like I have a ballerina figure and I glue the hands together, right? That's my ballet pose. Then notice that obviously like geodesic distances change wildly, right? Like if I started with these 2 points, the geodesic path went like that before, and now it cuts across. The PDE theory for small necks says for operators like Laplacian, if I construct a surface by this little gluing operation, then basically eigenfunctions are just the eigenfunctions of the 2 glued together pieces, like only slightly changed, like there's a perturbational theory there. So the argument they make in this paper, for better or for worse, is that like this thing can be stable to small changes. So for example, if I make a topology mistake when I make my 3D scan, like I glue together things that I shouldn't have, which happens, like if your arms are at your side, this thing is less likely to be affected than geodesic distance. Now that's what they say. Like the theory and practice here, it's not clear that they align, but it is an interesting property. If you want a geodesic distance, one way to compute them is using Laplace operator. So an interesting thing here, if you take a pinpoint of heat and you diffuse it for a tiny amount of time, if you look back at this heat kernel thing that we had before, so now you have 2 different points, x0 and x, and you look at the limit as t goes to 0. This quantity obviously goes to 0, but if you divide by the right normalizing constant, it doesn't. And in particular, there is this really handy formula here. This is called Verdun's theorem, which actually says that you can get geodesic distance between pairs of points through the heat kernel. I can never remember this formula, so the way that I usually check it is like on the plane. The heat kernel is just a Gaussian distribution. And of course, if you take log of e to the minus distance squared and take the square root of that with a minus in there in the right place, you get distance. So that's sort of what's going on here. And yeah, so this is Verdun's theorem, and there's this nice paper, Geodesics in Heat, from Keen and Crane and Company, 10 years ago, which basically proposes computing geodesic distances by doing exactly that. So they integrate heat diffusion forward a tiny amount of time. They take the log of that thing. In principle, that would already be geodesic distance, but it turns out it's super noisy. So then they have some sneaky ways to kind of correct it. So in particular, they take the gradient of their noisy distance function, and then they find the thing whose gradient is that. They sort of, because they know the gradient should have unit norm, they can like clean it up a little bit. Basically, steps 2 and 3 of this algorithm are engineering, and step 1 is Verdun's theorem. So I'll let you guys look closely at this paper. This would be a good one for your reading assignment, because it's a very simple technique, and it's very easy to kind of see how it's justified. A funny story, I gave a talk, one of my old research papers builds on the same theorem. I gave a talk in a room at NYU talking about this classical theorem from old geometry written by a bunch of old dead people, and it turned out Verdun was in the room, which is, I did not realize. He's just a professor at NYU. Yes, Anna.
If you go back a slide, because you said step 1 would already, like for a small t,
That's right.
you would integrate it and that would give you geodesic distance. But like there is a log in Verdun's formula.
That's right. So like if you did diffusion for a small t and then just took the log of that up to square root and sine, you would get distance, right? So in principle, steps 2 and 3, right, like they solve a second PDE, are unnecessary, like if you had a smooth surface. But the problem is that you're diffusing for so little that the diffusion is usually smaller than like the length of an average edge on your mesh. And so there's a lot of problems with that. So empirically what they find is that if you take the log of a small amount of diffusion, the gradient of that function appears to be reliable.
You're just allowed to move this limit inside of the loop.
No, these are all approximations. Yeah, these are. Oh, yeah, you certainly can do that. You can move the limit inside of. You have to be a little careful. Obviously, you can't move the limit past the t outside of the log. But that part is okay. What's a little bit tricky is they find that in like kind of on average, the gradients of that function are okay, but locally they're not. And so they find that like kind of reintegrating them after normalizing improves distance function. But that's empirical. Like steps 2 and 3 here are experimental. Yeah. And in fact, actually, if you look really carefully at this paper, there's an interesting theorem that they prove on meshes, which shows that this thing for a really small t converges to the wrong value, which is kind of surprising. If you read the theorem closely, it says that it converges to shortest path on the graph of edge lengths, which, as we talked about, is actually not the value you want. So there's an interesting balance to be had in this paper between you want t to be big enough that you integrate like a meaningful heat problem, because otherwise you're in like little tiny numerical domain. But if t is too big, this approximation breaks down. So there's like some funny bias variance trade-off happening there. There's a fantastic set of numerical analysis problems that are hiding in this paper that somebody needs to go back and solve. But this is a very well-known research paper in geometry and widely used. So there's a lot of, it's worth studying. As promised, we're not going to hit machine learning applications today, but we'll do that at the beginning of class on Thursday. Just a few more applications in low dimension. I think you actually implemented this on your homework, but you can use it for smoothing out surfaces. This makes perfect sense because remember that Laplacian of your coordinate gives you gradient descent on surface area, right? So if you have like a really noisy surface, it's trying to kind of smooth that stuff out. This is called mean curvature fairing. And in fact, in your homework, you even kind of derived this nice integrator for it. It's used for mapping surfaces into the plane. I think we'll skip this because we're low on time. But essentially, one of the principal ways to do surface parametrization in computer graphics is to maybe pin the boundary of the domain and then solve Laplace equals 0. And notice that makes this parametrization where like every vertex is at the average of its neighbors, which is a really nice property to have. And in fact, if this were a geometry processing course, we would spend some time proving a theoretical result, or I would, because I tend to teach theory-oriented classes. There's the following, which you should all look up and read, which is Tut's theorem. Apparently, you really do pronounce it Tut and not Toot. He's English, but in any event, Tut's theorem says that procedure creates an injective map. Like you can't have a triangle that flips over in that process, which is why the graphics people like it. And there's so many others. I mean, here's even more things. Like people use it for shape retrieval, quad meshing, deformation. All these things are different applications of that same matrix. Okay? So with that, in our next lecture, we will continue with our discussion of Laplacian. Isn't this fun? I love Laplacian. In our next lecture, we're going to talk about high-dimensional applications of Laplacian in machine learning. Actually, conveniently, I didn't do the point cloud Laplacian anyway, and the main application of that is in machine learning. So it'll all fit together. So that's our plan for next time. So with that, good luck on your homework. I expect I'll have a jam-packed office hours tomorrow morning, and see you Thursday.